Yes, ma'am.
We don't have anyone to say street running down here.
Let's see. Chapter 12. Well, at least one person showed up from the right side of the room.
Blake's probably waking up from the other task, right? Cause,
He's got a class before this.
oh yeah, they had the test today.
Jesse, no excuse.
They tested once.
Applied EM.
What do you mean? I'm here at 3 o'clock. It's 3:01 now, but it was 3 o'clock when I walked in. I don't
Anyway,
need an excuse.
let's move forward with our example problems for today. So, starting with 12-5. Determine the deflection of end C of the 100 millimeter diameter solid circular shaft. The shaft is made of steel having a modulus elasticity of 200 gigapascal. So we're doing a deflection problem. So, where do we start? All right, let's go with free body diagram. Here's my shaft. All right, and we have 6 kilonewtons pulling down on this end, and we have, that's so here and here. We have 2 meters, 1 meter. So, and we have reaction forces. We have A. So we have an A reaction force and a B reaction force. Okay? Now what?
Solve for reaction forces.
Okay, by taking the
Solve the forces, solve the moments.
some of the moments about what point? So we have 2b minus 6, or 3 times 6. 0, so then b is equal to 9. And sum of the forces and the y equals 0 equals a plus b minus 6. So a is equal to 6 minus b, so negative 3. So that means a is pointing downward and b is pointing upward, and they are 9 kilonewtons and 3 kilonewtons. Okay, now what? You missed your free body diagram. Now what? Okay. I'm not going to erase it into there, I'll just draw it like this. It's 2, it's 3, that's 0. Okay, what's my shear moment diagram look like? I'll start B. Where do we start? Positive 3?
No, negative.
Negative 3?
Negative 3. Because you want the positive shears rotating counterclockwise, right? It's rotating clockwise?
Positive shear is rotating clockwise.
Yeah.
So if you look at this, here's my end. This is pulling down, that's 3. To compensate for that, I have to have an upward V.
just counterclockwise.
Right, my V has got to be that way.
Yeah.
So it's counterclockwise.
Yeah, negative. What's this here?
Didn't I say, is that what I said? That it should be negative? I mean, the clockwise, because it was, where the heck is mine? Where am I in this? Where was it? I didn't say negative. Excuse me. I thought clockwise was positive, right? Isn't that clockwise?
That's counterclockwise.
Oh, no, it's counterclockwise. Never mind. Okay, yeah, you're right. It's fine. Sorry. Okay.
So then it goes all the way to 2.
Goes horizontal across
Yeah.
to 2, and then what happens at 2?
Goes down.
Goes up to positive 6.
Goes up to positive 6. Over and down. Right, so that's 6, and that's minus 3. All right? What's the moment diagram look like?
Upside down here.
What's that?
And upside down.
An upside down pyramid. So it starts at 0, goes down to what?
6. Negative 6.
And then back up to?
0.
Okay, it's a little asymmetrical to call it a pyramid, but all right.
Hey, you know, not everybody's perfect when building their pyramids.
Okay.
Have you seen the trailer for the new Minion movie?
I have not.
They build a pyramid and it's upside down and they christen it with the bottle of wine and
And
it falls
falls
over
over.
and kills everyone. And
That's very nice. All right. Anyway. Okay, so those are Sherman moment diagrams. Now what?
Find our, so now we're gonna use our max moment. And our,
Next.
I guess I should probably read the question.
We're supposed to be finding the deflection of the NC. So what do we need?
So we can just, so, we just find M of X, M of X.
M of X. Okay.
Wait, if we're constrained from B at B, can't we just separate our free body diagram, cut it in half from B to C, and then draw our moment there? Or do we not gain anything by doing that?
I'm not sure I understand what you mean.
Why wouldn't we draw our moment diagram from B to C?
Well, what's
A
my
to B is
curvature going to
one.
look like here? What do you think my curvature is going to look like? Right, if I were going to draw my elastic curve, what's my elastic curve going to look like? We're going to start here,
Continuously curve off, slightly,
like this. Is
yeah.
that what you're saying?
Yes.
Okay. It's going to look something like that. Right? So I don't really know what's going on.
It's not discontinuous at B.
There's no, the elastic curve has to be continuous. Right, as we've talked about, we know continuity has to occur at each point. It has to be a continuous elastic curve. Right, because this is actually the physical position of the beam. The beam can't experience a discontinuity. Okay?
So, could we just analyze the beam though from B to C? Because we know that it's fixed at B.
You have to find the force for B, and then by that time you already put on the free body diagram for the whole thing, so you might as well just do the whole thing.
Well,
Right.
the thing is that we don't have to take this integral so many.
We can try it. We can try it. Okay. Let's do the whole thing first. And then we'll see why we had to do the whole thing. Okay. So we have m of x. Look at the picture. They give me an x1 and an x2. So presumably, I'll want to have an m of x1 that applies from A to B. And separately, an m of x2 that applies, as you can see on the graph, from C to B. Remember I said last time that you can define your x's wherever, however you want to get your curve to fit nicely, and then just make sure that the continuity at the place where those two functions join one another is sufficient. You guys remember that? Okay. So we're going to have m of x1. What would m of x1 look like? Well, that's m of x1, that's this region.
Negative 3x.
So it's just minus 3x, right? Minus 3x1.
It's plus 6x.
What is m of x2? Look at the drawing. Look how x2 is defined.
Oh.
So it'd be
Right, negative 6x2. Because x2 is starting over there on the at C and coming back to B.
Right.
So with a progress of 1 in the x2 direction, we have a movement of negative 6.
Is there any special reason why we did that, or why didn't we just go left to right?
Because it's a lot easier to define minus 6x than it is to define plus 6x minus 18. Right? But if you wanted to do plus 6x minus 18, that's fine, we just call x2 different, we'd have a different x2. My x2 would be defined from B to C.
Yeah. Why would it be minus 18? Just
Well, if it was from back here, if x was the same, if x2 is the same as x1, they both start at 0 back here, the y-intercept would be minus 18.
Oh, okay.
If it was here, it'd be minus
Yeah,
6,
okay.
right?
Yeah. Got it.
But they've defined it for us in the problem, so we're going to go with what they gave us. Okay, and you can see this is obviously an easier function.
Yeah.
Okay, does that make sense to everybody? Are we doing it that way? Okay. So m of x1 and m of x2. Now what do we do? Now we know m of x. M of x. Now we recognize that m of x is equal to ei d squared v dx squared. So the slope is the integral of m of x, right? Actually 1 over ei times the integral of m of x. So, what's the integral of m of x? 1.
Over 2x squared.
What's that?
3 over 2x squared.
Oh, well, minus
3 over 2.
2 over 2 x squared, x1 squared, plus c1. And we have a constant of integration, right? And then v is 1 over ei times the integral, well, it's not true. I should just do it this way. Why don't I just do it this way? Okay? So I'm just, integrating all of that thing. So ei times v of x is equal to the integral then of minus 3 halves x1 squared plus c1 dx. Right? Okay? I'm just integrating this right-hand side, integrating both sides with respect to x. So I integrate this thing, ei comes out. I'm just leaving the ei on the left
I
side.
see what you're saying.
Okay. So we just keep the pure integrals on the right. We can put the constants where we want to. So what's that? minus 1/2 x1 cubed plus c1x plus c2. So we have two variables of integration.
Can we just not combine?
No, because c1x, right? We had to integrate c1,
Oh, yeah.
right? Okay. Right, so, and m of x2 is basically twice m of x1. So we'll get similar curves, EI, dv, and probably make these dv1, dv2, dx is equal to twice what this one is, which is minus 3 x2 squared plus c3, and EI v2 of x is going to equal minus x cubed, x2 cubed, plus c3x plus c4. Does that make sense? x2, sorry, I put myself x2. Okay? So now, we've got 4 unknowns. C1, C2, C3, C4. We care about x2 piece, the x2 piece, so maybe we can just solve the x2 piece. Can we use boundary conditions to solve for, I should have asked you, how are we going to solve for these variables of integration? We're going to use what? Boundary conditions and continuity, right? So, what are the boundary conditions that govern this piece?
B equals 0 at A and B.
At what?
A and B.
Right, but just from this side of the equation, just from this piece, from the x2 piece, what do we know? What boundary conditions do we have for x2?
X equals 0 and x equals 2 equals 0.
At what value of x2?
Oh, x2.
Right? This is all in terms of x2, right? You said this is what we wanted to do first. Right? You told me maybe we just try this BC piece.
X of 1 meter equals 0.
Right, so we know that x2 equals 1 gives me a v2 equal to 0. Follow me? At x2 equals 1, v2 equals 0. Okay, so now I know that this is equal to 0 at x equals 1. So if I plug in 1, then I get 0 equals -1 plus C3 plus C4. Right? So all I know then is that C3 plus C4 is equal to 1. But that doesn't solve my, I don't know what C3 and C4 are. I need another boundary condition. Do I have another boundary condition that I can work with on the right-hand side?
On the right-hand side,
Can you say it?
0.
3 equals 0?
At 3 it equals 0, at x2 equals 3? No, because this function and this function are different
Yeah.
functions.
Yeah, at x equals 0 and with x equals 0.
Yeah, so that doesn't help me though, because m of x is not in my final expression. Right? I need something that includes this expression so I can get C3 and C4. I have to know something about this, or potentially about that. Right, because I've got to do something that includes C3 or C4. My expression for m, well, I don't want to have, I guess m is here. That doesn't help me any. Right, because that doesn't give me a value for C3 and C4. I have to know something about the slope and the position in order to get,
Oh, the slope
So I don't know anything. Yes.
So if you're taking integral of the moment of x1,
Mm-hmm.
we already know what the area underneath the, it's 1/2 base times height, 1/2, 2 times -6. Could we plug that in, and then x would be 2
So,
for C1 or C3?
so that doesn't allow for the fact that, so for instance, okay, if we came in here and said, x equals, you know, that's a, excuse me, it doesn't give the functional behavior. If we calculate the area of the section, it's 3. Because if we plug in x equals x1, we get 3. That's -3. But that doesn't tell us anything about C3. It doesn't tell us anything about the variable integration because we don't, if there was a constant in the slope, when we differentiated that slope to get this, we would not, the constant would go away. It wouldn't be a part of the derivative, right? That's the way variable of integration works. It's because when we take the derivative of that, we would get 3x, or 6x2, rather, we would get this function, but we wouldn't get any kind of
Right.
information about the offset.
Right. So if you do that, basically you make C1 irrelevant.
You would make
But-
C3, you're
C3
arbitrarily choosing C3 equals 0.
Yeah.
You just find the
Yeah.
area in here, that's not the case. Okay. So the point is, we only have one constraint over here, one boundary condition that's helping us. And so we can't solve for two equations with one unknown. Or I'm sorry, two unknowns with one equation. We need two boundary conditions to solve for the two unknowns, or two constraints,
So I guess I have another question too.
okay?
How come we can't just integrate from like 1 to 0? Because
That's what he just asked. If we integrate from 1 to 0, we don't get back C3, right? Integrating from 1 to 0, doing a definite integral doesn't find our variable of integration. And that's what I said, explained it going backwards. If I take the derivative of this expression,
yeah.
it doesn't matter what C3 is, I'm gonna get that function. That function is the derivative of this expression no matter what. Right, it's whatever C3 is. I take the derivative, C3 goes away, and I get that function. So for all possible C3s, that's the function. Do you remember this one?
No, yeah, okay, I guess, okay, yeah. So if we were to do a definite integral from 0 to 3 of this system and just split it up with the two functions on each side.
Right, we do definite integrals, the C3s get subtracted out. That's why we don't have to worry about the constant of integration when we do a definite integral,
Yeah.
right? But when we're doing an indefinite integral, the C3 doesn't, we have to keep that in there. Okay. Are we good now?
Yeah.
Okay. So we have two unknowns, we had one condition, one boundary condition, one constraint, so we couldn't find for both unknowns. So we have to go back to the first set and use boundary conditions there, hopefully. That will give us another bit of information we can use over here. In particular, what we know about the continuity of the bar is that whatever the slope is at point B from the first side has to be equal to whatever the slope is at point B on the second side. See what I'm saying? So we know the slope has to be continuous across the boundary. Because we know the position 0 already. So if we can solve for this one and figure out what the slope is at that intersection, we can use that slope to solve for C3. And then using that C3, we can solve for C4. Does that make sense? Okay. So let's go back to this expression here. What are the constraints we have for the left side? What are the constraints we have for the V1 side?
Once again, at x equal to 0 and x equal to 2, v equals 0.
So those are our two constraints, at x1 equals 0, v1 equals 0, and at x1 equals 2, v1 equals 0. Right? So at x1 equals 0, I am left, this thing here becomes 0 equals C2. Right? And at x1 equals 2, 0 is equal to minus 1/2 of 2 squared plus C1 times 2.
That'd be cute.
Cubed, sorry. Okay, does that make sense? So I get 4 is equal to 2 C1, or C1 equals 2. So these are my constraints that side. C1 equals 2, C2 equals 0. Now, how do I get a constraint that applies to that side? I go to the intersection between the two. And I know that at the intersection between the two, V is equal to 0, but I've already used that once here. I've already used that constraint here. I knew that V2 was equal to 0 to x2 equals 1. But I also know the slope now. So the slope of this side, so I got this equation. I probably should have done these in separate colors. So I know that minus 3/2 x1 squared plus c1, which is 2, is equal to EI dv1 dx. And that's got to be equal to minus EI dv2 dx. Because the E and the I are the same. Does that make sense? What did I just say?
EDI is the same.
What does that mean?
Forget what E is, but I is the moment of inertia.
He's the modulus.
He's the force.
So why does this make sense? What am I saying with that?
Well, what you're saying is that the slope is the same at that one area where you're switching between your first slope equation and your second slope equation.
Okay, but there's a minus sign in there. Why is there a minus sign?
Because your position is going negative as you go from left to right across that boundary.
No. What were you gonna say, Gail?
Because when you look at the slope with this way, being your x is positive this way and your x being positive this way, that flips.
All right, so one is traveling left to right, one is traveling right to left. So the same slope would be viewed as a down slope on this side and an up slope on that side, or vice versa. So it's not just a matter of setting the slopes equal, but the slopes have equal magnitude but opposite in direction, because in this case we've come from x1 and x2 opposite directions. Okay? So if this is the case, then that's got to equal minus EI dv2, so that's got to equal, so what I end up with then is minus 3/2 x1 squared plus 2, evaluated at x1 equals 2, is got to be equal to minus negative x2 cubed, no, sorry. What did I do? Oh, minus there, minus 3x squared, x2 squared, plus c3. Evaluated at x2 equals 1. That make sense? Okay? So I can plug the numbers in, and I get minus 6 plus 2 is equal to 3 plus C3. And minus 3 is minus 7 plus 2 is negative 7 equals C3. So C3 equals -7. Oh, it was minus, this is a minus. Sorry. Positive 7 equals C3. Okay? And then, once I know that, C4 is equal to 1 minus C3 is equal to 1 minus 7, and therefore equal to -6 kilonewtons. Put the units in there. No, it's not, well. Yeah. No. Yeah, the units depend on where they are. So you'd have to go back and.
What do you mean by that?
So in other words, if you look at this last expression here, right, this is in
I see what you're saying.
kilopascals,
The units of
units to the
the
fourth
constant.
times units, we have unit to the fifth times, so this is cubed. This would be in kilonewton meters cubed. So C4 will be in kilonewton meters cubed, C3 will be in kilonewton meters squared.
Is C3 the same number throughout?
C3?
Yeah, even though the units are gonna change in between,
No, this is still, this unit, the units here are unitless, this is unitless,
no, okay.
right? So here we have kilonewton meter squared, this is kilonewton meter squared. And then down here, this becomes kilonewton meter cubed, which means kilonewtons meter squared times meters. Okay. So I have so now I have all the values. 6, 7, 0, and 2. -6, 7, 0, and 2. Okay, got all my C's, what do I do now? What am I looking for?
Plug into the equation and solve for
Plug into which equation?
our second equation, or our bottom one, the v of x. equation.
Right. Plug those values back into here, because we're trying to solve for V2 of x. So V2 of x is equal to 1 over EI times x2 cubed plus, or I'm sorry, minus, I didn't see, no, plus 7x2 minus 6. And then plug it in at what value of x? What value of x am I going to use? x2. 0. Plug in x equals 0. Well, that's easy, because that goes away, that goes away. So I'm left with minus 6 over EI. And this is in, again, kilonewton meters cubed. And this should be in kilonewton meters squared, which it is. So 6 times 10 to the third Newton meter squared divided by E, which is 2 times 10 to the 11th times I. What's I?
Like, what's the actual formula for this?
Yeah, what would be the formula for I? What kind of a beam is it?
Circular, isn't it?
Circular? What's the moment of inertia for a circle?
1 over 4.
Pi over 4 maybe?
5 over 4, yeah.
R to the fourth.
Is it just r to the 4th?
Yeah. So 0.05, because it's 100 millimeters diameter, so 5 centimeter or radius squared to the fourth. Anyway, all right, and that gives me negative 0.05 negative 0.006112, or 6.112 millimeters. And it's negative because it should be negative because the movement's deflected down. So, everybody follow that process through. We find the moments, we integrate the moments on both sides, yielding in this case, four different constants of integration. And then we have to solve for those constants of integration using the boundary conditions and the continuity equation. And then, once we have those, we go back and solve for the thing we're actually.
What did you write up there? You got negative 6 something.
Times 10 to the third, sorry. Because it's 6 kilonewton meters cubed. Times 10 to the third. Is that what you're talking about? Okay, so everything's in SI units that way. Okay? So, you ready to try another one? And there are going to be times, like this one's probably one of them, where you didn't necessarily have to draw the whole shear moment diagram to find those relationships. I mean, I probably could have looked at this and said, as I move along here, the moment, there's no, the moment is just 3 times whatever it is, my distance. Right? And I move along here, it's going to be just 6 times whatever my distance is as I move from right to left. So you probably can, in some cases, as long as you get the sign correct. All right. You don't necessarily have to always draw a shear moment diagram.
They are fun to draw.
I suppose that depends on your idea of fun. All right, now we have a pipe. It can be assumed to be roller supported at its ends. Okay, so the roller supported meaning that there can be no, there's no lateral constraint, there's only just vertical. There's just a vertical load bearing element at the ends. And by a rigid saddle at the center C. The saddle rests on a cable that's connected to the supports. Determine the force that should be developed in the cable if the saddle keeps the pipe from sagging or deflecting at its center. The pipe and fluid within the fluid within the pipe have a combined weight of 125 pounds per foot, and EI is constant for the pipe. Okay, so everybody understand the problem? You essentially stretch a cable between the two walls, and the tension in the cable pushes up in the center to create a force to counterbalance the sag so that the center doesn't move. Okay? So what we're going to do first? Kayla, what are we going to do first? All right, see, we're just letting people steal your stuff. Free-body diagram. All right, what do I get? What forces have I?
Water reaction forces at A and
A, B,
B.
okay?
A distributed load across the whole pipe. About 125 pounds per foot. And then a support this.
Okay?
I don't quite understand the picture. So there's a pipe that's full of fluid and its own weight, and then it's resting on a cable in the middle.
There's a saddle in the center that is resting on a cable.
It was the saddle, just that little piece.
That little piece, yeah, the little, you know, like a little, it's a little piece shaped like this.
Like, oh, okay.
See what I'm saying?
It's just weird, it's just a weird construct.
I mean, that's how you provide the additional support for a pipe. Put an extra piece of cable under there to help support the pipe. Because and the presumption here is that the tension in the table can support tremendous tension, but the pipe can't support any kind of static.
Bending, yeah, so otherwise it's going to crack or something.
Okay? All right, and then let's put some dimensions in here. 12.5 feet. This is 12.5 feet. And then saddle distance here, even though I've not shown the saddle, is 1 foot. Okay, what now?
Let's do a shear diagram.
I don't think we're quite ready for shear diagram.
I guess we have to some are reactions.
So we gotta find something.
So maybe do one of some forces and moments.
Okay.
Acceleration force in the y direction equals, how we have it drawn, A plus C equals B minus 125 times
X or Y, whatever you want, whatever variable you want to use.
No, I mean, we got 125 foot
times 20.
pounds per foot times 25 feet.
Oh, you don't want to just do it from one end to the other? Like you just
I'm
say,
trying to find a reaction.
I guess, I don't know, don't listen to me.
What do we know about A and B?
They're gonna be
Semi equal.
Right, we have symmetry in the problem. Right. So we can call A and B just some generic F. And 2F plus C minus 25 times 125. So 2F plus C is equal to 25 times 125, 3125.
we can do a moment. Simple smart limits. About A. Oh, what if we do moment on C?
All right. Equals what?
Equals 0.
Okay, but I think you're gonna,
Don't you just have A equals B?
yeah, that's all that gives you A equals B.
Yeah.
All right, so sum of the moments about A is equal to 12.5 C plus 25 B, 25 F, change it to F, right? Minus 12.5 times 3125. What's that?
Sorry, I was just saying what was going through my head.
Okay, so it's probably easiest to divide that through by 12.5, and we end up with C plus 2F minus 3125 equals 0. Oh crap. We're back to where we were before.
No, because we can solve for C or F and then plug it into the other equation.
No, it's the same equation.
The same, correct.
That'd be nice. Just copy the equation down twice.
That would be.
Any number equation, oh, let's write it again. Okay, so
Maybe a third time.
bottom line is we can't solve for it. Okay, we can't solve, yeah, well, to this point anyway, it's not, it's indeterminate, but we have other constraints. Right, in terms of just the forces, it's indeterminate. Right? This does statics can't solve the problem for us. But beam deflection can. All right? So, what's the moment going to look like? Let me put my, we're going to have to draw my elastic curve. That's my elastic curve. Okay. So, what shall I do?
I would guess just the moment diagram, or shear moment diagram.
Okay, let's do a shear moment diagram. And those are our 2 points. Okay? What's my shear on the left? F. Positive or negative? Positive. And so, because on the left side, this is pushing up, so this is pushing down, which is turning clockwise. So positive F. What happens as I go across?
Linearly down.
Linearly downward to what?
Oh, 12.5 times 125. Right, that's the area underneath there. So whatever,
Yes.
yeah, and then C goes back up, and then it goes back down, and then it goes up again.
So it goes down to what?
To 125 times, it's F minus 125 times 12.5, which I don't remember for that though.
So will that be a negative value or a positive value?
It should be below.
Right, we don't know.
Because we don't know that.
Yeah, but we kind of know, we can guess.
Oops.
Because then that one's gotta be below. It's gotta be
Is
F.
that what you're saying?
No, that one has to be F below, that way it would be, it's going back up. So C just has to be smaller.
So you want me to draw this? You want me to end, where do you want me to end?
Okay, it needs to look like it has to slope down underneath the axis. Go up, then slope back down underneath the axis.
Where do you want me to end is what I'm asking.
Then go back to zero.
He wants you to end it negative.
Negative.
Negative what?
Negative. B.
Oh,
Not
negative.
negative.
Why? Oh, yeah, I guess that, wait. Yeah. Weird ending.
So I got something that's gonna look like this. Didn't draw that very well.
It's so abstract.
Right, something like that.
Yep.
Right. Okay. You want a moment diagram too, right?
Wait, why did it connect back to zero?
It does.
I mean, it would at the end. Go
Oh,
up like
okay.
this. And this one comes down to zero, but yeah. Okay.
Technically, at least.
Can we solve for C then? Because we know C is equal to 2F.
No.
You can't solve
We
this.
could do, the curve could look like this. We have no idea what's,
You know how far it's going down.
C is equal to 325 minus 2F. Right?
Yeah.
So here's the thing. Oh, I'm sorry, go ahead. So what would the moment look like?
Oh, sorry. It's
Concave up or concave down?
Concave down, it's gonna be up, and then you're gonna go down. You're gonna go to the negative,
Back.
then, it's just the exact
It's just the
opposite,
mirror,
like
yeah.
a sine function or something.
Is that what you're saying?
Yeah, that's what I'm saying. Actually, I think it's like a little,
Doesn't matter, it does something like that.
yeah.
I don't know where this peak is. This could be on top, it could be on the bottom, I don't know. Okay. All right. All of that's not really a whole lot of use,
Well, rats.
because I don't have values for any of these. Right? I don't know where any of these numbers are. I know it has just general character, this general shape, but it doesn't have. So really, I've got to come in here on this end. And just describe it in terms of F. Right? The moment, at the internal moment at that point, is equal to F times X, right, minus 125 times X times X over 2. Right, because this distance here is X. I got 125 times X worth of force pushing downward. Right.
For the moment,
So 125 times X is the total force, and the position of that is at X over 2. So my expression for M is going to be Fx minus 125 over 2 x squared. Okay? That's really what I want to do. I want to give an analytical expression for it, and doing the shear moment diagrams, that's what I said earlier, you don't always get to do the shear moment diagrams. Sometimes you just have to look at the picture and figure it out from that. Okay? So then, having this, we'll go through the same process, we'll pick that up next time. We'll pick it up next time where we left off. What's that? Next month. I'm sure we'll all have it fresh in our minds.
Wait, will Josiah watch this?
Me?
Happy Thanksgiving, Josiah.
Of course, the next person who takes this class independent study will also be looking at who's just on.
They can stop me.
Yeah, I'll figure. She's.